able to attend now. Okay, so we can start now. So I said I was thinking we start from just the first topic. I wanted us to go back to the measurements because I saw that when it comes to the work, people are giving different solutions, and you can check for the transcended accounts. We have about 3 accounts that are in, so try to check for one. You find it. There is no audio coming from there. It's muted, so you'll be able to see the board. Okay, so this night, remember you said our classes are going to be lasting for 2 hours. So some of you are like, no, want study time. Okay, so you can study, but make sure the time that you join our class, you should consider that to be studying as well, so that you get everything that we talk about. And if you do that, I can assure you, you'll be doing well in your quizzes and the tests that you're going to be having. As you've seen, we'll be dealing with the tutorials. Okay, so now what I'm going to do is the first 30 minutes I'm going to explain the measurements, how to go about the units, conversions. We'll talk about accuracy and let me just say uncertainty in measurements. Then we get from there, then we have to go back to stoichiometry then. Okay, so look at different things so that you're able to understand, because when they give you a question in chemistry, they'll give you a question without asking you for the number of significant figures that they want. But whenever you attend, they expect you that you should give the same answer rounded off to the same significant figures, meaning that there are some guidelines that you need to know. Okay. So basically, both in chemistry and physics, we deal with what we call quantitative measurements. Quantitative. So quantitative is a word that comes from what? From quantity, right? And quantity actually denotes or tells us like the how much of something, right? Quantity, how much of something. So under measurements, we're going to deal with quantitative observations that we get to have. Okay, so basically when you're dealing with a measurement, you expect that there should be a size as well as what? A unit. Okay, so there should be a size and also a unit. That is a measurement. Because if I just say 40, you are not going to understand what I'm talking about. But if I put a measurement, for example, if I put 40 meters, if I put 40 kilograms, this now has got a complete what? A complete meaning, because there is a unit as well as what? A size. And from if you get it all as a measurement, you'll be able to get a full meaning. So if you look at this, you know that I'm talking about length. If you look at that, you know I'm talking about what? About mass. Okay, so we need to know that we have got different units of measurement. So for example, if I talk about mass, we know masses can be measured in different units. It can be measured in grams, it can be measured in kilograms, it can be measured in pounds. What else can we use to measure mass? Of course, the milligrams. I can also put micrograms. Yeah, so we have different units that can be used for almost all the measurements that we have. So to make the things easier, the scientists had to sit down and came up with what we call the SI units, the international system of units, so that as you get to move from one country to the other, you'll be able to understand and be able to interpret what your friend is talking about. Of course, that has not been so effective, because if you go to some countries, for example, they are going to measure your height by looking at usually they get to tell you, maybe they look at they use what we call feet sometimes. Yeah, others may, of course, us, I don't know what we use, if we use meters, because we don't usually talk about our heights, but I can say meters. Then we have different ways of measuring the height. Okay, so basically that's what we're trying to say. Then, like for example, in most of the countries, the United States, they get to use things like for distance, they will use miles. Then here we are more conversant with kilometers. But of course, there is a guideline for the SI units, and that's what we are going to be working with in physics, so that wherever you go, where you're going to meet a physicist, you'll be able to understand one's language, and or a chemist as well, because basically we are in chemistry. Okay, are we together so far? Are we on the same page? Okay. So just as in physics, we have what we call basic or fundamental quantities. So these are, I think from my school we've been saying there are, is it 7? There should be 7. So you should know them. Know them and know their standards or the SI units. Look, of course, this content looks simple. Most of the time people try to put it away, but they end up losing marks in chemistry. Physics, they are not so strict when it comes to the figures, but in chemistry, they pay much attention to the way you present your solutions in terms of the figures, how you get to run them off. So it's very important that you get to understand what you are saying here. Okay, so among the 7 quantities, physical quantities that we know, we have the mass. What else? We have the length. We have time. We have temperature. These are things that you don't have to, they don't depend on other things like a formula. It's just something that you can measure just using a different apparatus on its own. Then there's also electric current, and of course a more of a substance. Are they already 7? There's one more remaining. So there's also luminous intensity. Of course, that is under light. Okay, so these have got what we call standard SI units, and they are the ones that are going to be helping us to come up with the standard units for the different measurements that we get to take. So for mass, what is the standard unit for mass? It's kilograms. For length, what is the standard unit for length? Meters. Time, seconds. Temperature, instead of Celsius degrees, we get to use Kelvin as chemists. Electric current, what do we use? Okay, ammeter. Ammeter, isn't that an apparatus used to measure? Is it a unit? Okay. Then the more of a substance. In fact, it's not actually more of a substance, but I was supposed to say amount of substance. Okay, so it's measured in moles, and that's what and this is what we're going to be talking more under in chemistry. Most of the calculations, whether it gets to thermochemistry, electrochemistry, you get to talk about moles are going to be throughout your course, even as you get to organic chemistry. Okay. You're saying you're unable to do it? Hello? Can you guys get what I'm saying? Somebody is saying they can't get me. Is that the same with everyone? Okay. So basically we have prefixes. These are of course things that come before a unit. For example, of course we've talked about length to be measured in what? We've said meters, right? So now there are some prefixes that you can add to meters to make it different. For example, if I say kilometers, it changes the meaning of meters. Okay? Somebody can also come and say maybe centimeters. It also changes the meaning of meters. Somebody can say millimeters, somebody can say micro meters, somebody can also say nanometers. So these are some of the units that are going to be meeting. Okay, so now it's up to us to get to understand what these prefixes mean, because when you're doing a calculation in chemistry and physics, they expect you to use what we call the standard units. Okay, so meaning that, for example, if I give you centimeters, they expect you to do what? They expect you to convert it to meters. So you need to understand what these prefixes mean. There's a question? You have a question? Somebody said something. I didn't get clear what they were saying. Alright, we'll move on. We'll move on. Okay, so these are some of the common prefixes that we need to understand. So when somebody says kilometers, what do they mean? How do we get to convert that directly to meters? Remember, I think, let me start with this. I think length will help us understand more. So we're talking about length, right? Get that. Okay, we're talking about length. So it will help us understand the prefixes that are there. I think I'll start with the common ones that we know. So when we say, of course, we are saying length is measured in meters, right? We agree. So now let's say we have a kilometer, 1 kilometer. What basically does it mean? What does a kilo mean? Is it bigger or smaller? It's bigger, right? So it's 1,000. It means that you're dealing with 1,000 of a meter. It's just a prefix that changes the meaning of something. Okay, how about if I say, maybe let me first of all get to the bigger things. How about if I say mega? Maybe I say 1 megameter. What does it mean? So I think this can get, if you go back to your something like MBs, like if you're dealing with the space, this is megabytes. Okay, so bytes is actually the unit that we use, but if you say megabytes, what does it tell you? It comes from what? So if I want to remember it, we can say it comes from a million. Excuse me. So meaning that it's actually 10 to the power 6 meters, right? Are we together? So there's a difference between mega and milli. For milli, we use a small letter to represent it, but for mega, we use a capital letter to show that it's bigger actually. Okay. Then the other one that we can talk about, we have what you, for example, if you get to the same space, we have gigabytes. So we can say, we can also talk about gigameters. So what does a giga mean? So it's a billion, right? So it will be 10 to the power 9. So these get to increase in by 10 to the power 3. So we started with 1,000, went to a million and that. So this is for the bigger things that are bigger than a given unit. These are the common prefixes that we get to use. Now, there are some that are smaller. I'll start with decimeter, with a dec. So when you say 1 decimeter, what does it mean? So 1 decimeter is something that is smaller than what? Smaller than a meter itself, meaning that it's supposed to now become 0 point something. So we need to know that 1 decimeter, or let me put it this way, we need to know that 1 meter is actually equivalent to 10 decimeters, right? So meaning that 1 decimeter is going to be 0.1 meters. So meaning that if you see a dec before any given unit, it means that it's actually making it smaller than 1. That's what it means. Then one common thing that we know is centimeters. So if you said centimeters, we know that a meter is equivalent to how many centimeters? It's 100 centimeters. So if you want to make 1 centimeter a subject, you divide a meter by 100, which will make it to be 0.01 meters. Are we together so far? Then after a centimeter, we can talk about millimeters. So a milli is now something making it smaller, and it's going to be, as you might guess. So we've talked about 10, 100, so it will be 1,000 now. So it's 0.001, or preferably I can say 1 times 10 to the power negative 3, meaning that you divide by 1,000. So when I say 1 over 100, guys, you should understand that it's the same as 10 to the power negative 2. Are we together? So if I say 1 by 10 to the power negative 3, I mean it's 1 divided by 1,000. That's what it means. I hope we're on the same page. Okay, so we've talked about MIDI. What else can follow? We can now move in there. We multiply by, we add 3 more zeros. It will now be 1 micro. 1 micrometers. So this one is 1 by 10 to the power negative 6. Then the other one is nanometers. So, madam, what you can do is check among the participants. You're going to find that there are about 3 accounts for transcended that are there. So check for the ones that are muted. You're going to find the board. Are we together? So basically these are the common prefixes that you guys have to know if you want to make your life easier. Okay, so let me try to give you a practical use of these units. Let's say they ask you to say maybe let's say under molar concentration, this is under stoichiometry. Of course we know that molar concentration is given by the number of moles divided by what? Divided by the volume in liters. So now let's say they tell you to say, okay, you have about 0.2 moles in maybe let's say 2 micro what? Maybe microliters, or maybe should I put it, yeah, microliters, for example. So what does that tell you? Of course, it is a requirement that whenever you are dealing with molar concentration, it's supposed to be moles divided by what? By liters. So you need to make sure that the microliters is converted to liters, because if you divide directly, your answer is going to be wrong. So that's why it is important for you guys to understand what these prefixes mean. And when they come to tell you 2 milliliters, what does it mean? So you know that this is a milli. So it will be 2 by 10 to the power negative 3 liters. For micro, you know it's times 10 to the power negative 6. Or you divide by a million if you want to. So that's the way to go. That's why it's important for you guys to know the prefixes. Are we together? Are we following? It's learning now. I don't know if you're able to get it because I'm using a mic, so it may be minimized a bit. Can you get the sound of the lens? I don't know. Okay. So we've talked about the prefixes now. So we need to understand that it's very important to know how to convert, like we've mentioned. So let's look at some of the examples. I've already talked about things to do with micro. For example, if I tell you convert, yeah, where is my pen? Okay. What are you saying? Are you talking about are you talking about the people that you are within your background? I don't know what you mean by that. Okay. I'm sure it was your network. So the class has been recorded so far, so don't worry much. I'll share the link after. Okay. So I hope we know how to convert now. 4 microliters to liters. What have we said? So that micro means smaller. So it's 10 to the power negative 6 liters. That's the easiest way to convert. Are we together? Okay. So another example is when they tell you to convert 10 kilograms to grams. What you can do is say this is the same as 10 times a kilo times what? A gram. So a kilo is what? 10 to the power what? Okay. So what's the way to go about it? It's not hard. Are we together? So these are the two ways to convert. I've talked about a one where you just bring it directly, okay? Or this case where you begin to show this. It's still the same. There is what we call uncertainty in measurements. So sometimes we just get to approximate the measurements that we get to make. Okay? So for example, if I'm trying to estimate maybe the length of a rope, I can say, for example, okay, I think it should be about a meter. Okay? I can say it should be about a meter, but I can add something. Maybe I can say maybe 2 meters. So I'm so confident that it's a meter, but I'm not so sure about the 2. Okay? I'm not so sure about that 2 there because I'm just trying to make estimations. The same applies even when you are using a ruler to measure something that is very small in terms of length. The first figure there is going to you are going to be very confident, but there is going to be a figure that you're going to be adding at the end there. You'll be kind of doubting. You're just trying to estimate. So we tend to call that you're uncertain. Okay? Uncertainty. You're uncertain about it. You're not so sure. Okay. So under this part, we need to understand the difference between being accurate and being precise. So we can say accuracy and preciseness. When do we get to say that the units of the measurements are precise? And when do we get to say they are precise and they're accurate as well? So you get to say a figure is accurate when, let's say, the true value is maybe, let's say, 2.4 meters, right? Then you come to measure, let's say your value you have maybe 2.39 or even maybe 2.4 itself. Okay? So in such a case I can say that you are accurate. Okay? You are very accurate because it's very close to what? It's very closer to the true value. That's in terms of being accurate. You are comparing what you've measured to the true value. Okay? So you can say that it's actually you are being accurate in terms of your measurements, right? But then for preciseness, when do you get to say you're precise? So let's say you take 4 measurements, right? You take 4 measurements. The first one you get 2.39. The other one you get 2.38. The other one you get 2.40. The other one you get maybe 41. So these guys are kind of closer to each other, right? They are closer to each other. So when you take several measurements and you find that they are closer to each other, we get to say that the measurements are what? We use the term precise. You are precise in terms of dealing with the measurements because you've gotten several values within the same range, not very different. Okay? Because the things that you are certain of are the same. The only differences are the ones that you are uncertain of, the ones at the end. Okay? So if we understood the difference between being accurate and being precise. Okay. Okay. So if somebody took these measurements and they ask you, in such a case we can say that the measurements were both accurate and what? And precise. Why are we saying they're accurate? Because they are closer to the true value. how closer or nearer it is to the true value. That's accuracy. Then you're saying you are precise because your measurements are almost the same. Are we together? These things are very different. These things are very easy, but most of the people don't take them seriously. They just get to, whenever they get in chemistry, first you just go to, okay, let me look at stoichiometry. But it's very important to understand every concept. Okay? Very, very important. Okay, so now, under uncertainty measurements, it's very important, like I mentioned, that we need to understand the rules for counting what? For counting significant figures. Are we together? So, as a chemist in a lab, when you are given something to measure, or maybe you are told to do a calculation in your test, whether they've specified the number of significant figures that they want, you guys should find the same answers, because you need to understand the rules. Excuse me. You need to understand the rules for finding the significant figures. Okay. So I think most of the people have got challenges when it comes to measuring the number, counting the number of significant figures, things to do with zeros, right? That's where there is kafuafwa. So when you have 2.41, 2.0, oh, no, okay, let me 2.1, we have 3. These guys, it's very easy for you to count the number of significant figures, right? So you can see that in the first figure there, how many are significant? 3. 1, 2, and 3. 2 are significant, 1 is significant. Now, let me give you this now. 0.01, 1.00, 1.01, okay, let's start. So if you're able to understand this, then we are done under significant figures. Are we together? So I'll start with this one. If you look at 0.01, how many significant figures are there? Wow. It's 1, 3. Okay, so we have what we call receding zeros, or leading zeros actually. So whenever we have leading zeros like that, these ones are just telling you the location of a decimal point. So they are insignificant. So it's only one significant figure. Are we together? They are only telling you where you find the decimal points. Then the ones at the end, are they significant? They are significant. Why they are significant? Why are they significant? Why should you indicate the zeros at the end? So are you able to check the participants that are in the meeting, madam? Check for the participants. Or what you can do is this. Madam S, what you can do is leave the meeting and join again. It's going to bring automatically. You'll be able to see it. Just leave and join again. Try that. I'm sure it will be able to tell you that Transcended is presenting. Okay. So when you look, okay. So what I'm trying to say is this. For example, if you say 20 kwacha, 0.0, I can't just put a 0 there for nothing. It means that they're representing something. They're representing you that this is 0 ngwe, right? So all the zeros that come after a decimal place, they are significant. Are we together? Okay. So how about this one? How many significant figures are there? Only one. Why are you saying one? Huh? Because there's no decimal place. Okay. What are you saying? Okay, okay. Thank you very much. Thank you very much. So how about if I said we have how can I put it? Let's say we have 3.4. Maybe let me do this. 3.0 times 10 to the power negative 3. How many significant figures are there? Only one? Okay, now the funny part is, so only two significant figures. Okay. Now, how about this one? Look at this one. The power is positive. They are what? Okay. Only one. Okay. Thank you very much. You're right. Only one. So that explains why if they tell you to say round your answer maybe to two significant figures and you find that your answer is maybe to two significant figures. Which one? This one. There's only one significant figure. So, okay, whenever you have powers, whenever you have these, you don't look at them. You only look at the numbers. Consider the numbers only. Okay. Whether it's positive or negative, just look at the numbers. Then this one. Pardon? Yes, 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 yes. And by the way, we're not looking at that. Of course, yes, they become. And you're right. 0.001. And the other one is going to be 1,000. Yeah. So zeros at the end like this, are they significant or they are not? So even these one are not. Provided there is no decimal point there at the end, they are not. Unless there is unless something like that, then they are significant. Okay. Then 0.100, how many significant figures are there? What are you saying? Okay, are we all in agreement? You are refusing. Mute your mic, sir. So I'll be removing you now from the meeting. If you are making noise deliberately, I'll remove you from the meeting. Okay, so if you look at what we have there, 0.100, how many significant figures are there? Okay, so we said zeros coming after decimal points are what? Are significant, right? Now that will also confuse you in the next one. So how many significant figures are here? Okay. Alright, thank you very much. Gotten the point then. So that's how you go about it when it comes to the issue of significant figures. So reading zeros are not significant. That's in summary. Zeros in between numbers are significant. Sharing zeros are only significant if they come afterwards, after a decimal point. If you have zeros at the end without a decimal point, then they are not significant. Are we together? Yes, yes. The what? One, two. Alright. Is that clear? Okay. So have we understood what we've talked about? Okay. What have you not understood, sir? This all takes you back to this. It takes you back to this question. How many significant figures are there? So because these are only showing you the location of the decimal point. Okay. Okay. So then we also have to understand some of the things when it comes to multiplication and division. What do you get to do when you're multiplying figures in a question? The question is asking you to multiply and divide. Maybe, for example, the question that was dealing with molarity, right? They ask you, of course, you're dividing the number of what? Moles by the volume, right? That kind of an operation. They say you've been given 0.20 moles in a question. Then the volume was given maybe to be, let's say, 0.05 liters. So how do you get to find the answer there? Of course you divide, right? So after dividing, what is our solution? What basically do we get to get there? I'm sure it should be 40. Try to do your calculation. What are you getting? Oh, it's 4 times. So you have got 4. So now what should be your answer? Should it be 4.0 or just 4? What do you think? Okay, so as you are arguing, arguing, you need to know the rule now. So the rule is that whenever you are multiplying or dividing in a question, the answer that you're supposed to have, you should consider the least number of what? Significant figures. So if you look at the first one on top here, how many significant figures are there? There are 2. Then in this other one, there are 1. So The answer is 4. Just 4. But if there was a 0 there, the answer would have been 4.0. Do we understand? Because then that would mean that you now have two significant figures in the question as your least number of significant figures. Are we together? Okay. Okay. So, of course, for addition fraction, it's actually an opposite case where you get to look at the one having more significant figures. Not really. Okay, not really. That would be deceiving. So, for addition and subtraction, the only rule that is there is when you are dealing with decimal numbers. Alright? When you are dealing with decimal numbers, you look at you're supposed to go for the one having more decimal places as your answer. Okay? You go for the one having more decimal places as your answer. That's the way it goes under addition and subtraction. That's the only rule that is there. Are we together? So, for example, if you are dealing with maybe you are adding to, let's say, 4.2 and 6.457, your answer is supposed to be in this way, in that form, up to, not that should be 4 significant figures, but it should have 3 what? Decimal places. That's with addition and subtraction. It's not looking at the number of significant figures, but you're looking at the number of decimal places. Are we together? Okay. So, as we are talking about the Achilles things, and yes. Okay, so I'm saying it's supposed to be the highest, actually. The highest. I don't know if you have a different information. Maybe it's up the lowest. Okay, let me try to confirm that. Then obviously it makes more sense. Okay. Yeah. Okay, thank you very much for that. So as usual, then let it be the least and not more. So you consider the decimal place. I think that would only be that is the only difference there. Not more but least, but we are considering the decimal places and not the significant figures. Okay, thank you very much. So under accuracy and preciseness, again, that is under uncertainty measurements. We also have to understand things like errors now. What basically are they? Some calculations that they can ask you to deal with, especially in your lab. They can ask you to say, they ask you, for example, you're trying to predict the concentration of an acid or a base, maybe in a titration reaction. Then they tell you that, okay, what your lab technician did and what they had predetermined as the concentration was maybe 2 molar concentration. Then you, as somebody doing an experiment, you come and get 1.8 molar concentration. So it's not basically that you're supposed to find the exact answer, because you're going to say you are actually deceiving them. So there are some errors that you're going to find. So you find 1.8, then you begin like doubting. So no. So because there may be questions like find the absolute error that they can ask you. They can also ask you to find the relative error in that very question. Okay. You can also find what we call the percentage error. Okay. So in a lab again, apart from you being able to calculate the errors there, they also have to, they expect you to know the different types of errors that are there. So there are some things that make you to make some errors also. in a lab. Okay, so we have different errors. Sometimes it maybe the apparatus that you are using to take measurements, or maybe it may be you yourself, a person, you're not so sure of on how to take measurements. But if it's sometimes it may be a fault with what the apparatus that you are using. Okay, so basically we'll talk about them. We have what we call systematic errors and random errors. But for now, let's try to remind ourselves how we get to determine the absolute error. So the absolute error, of course, is going to be found as a difference between the true value and what? And the measured value. So in this case, it's 2 minus 1.8. So whether you can also say 1.8 minus 2, but the fact that you put the modulus there, the answer is always supposed to be positive when you're dealing with errors, alright? You're always supposed to have a positive value. Are we together? Then for a derivative, the same concept of absolute error being divided by what? The true value. So the true value in this case was a 2. So divide the absolute error by the true value, what you're going to get is the derivative error. So you're comparing the absolute error to the true value. That's why it's derivative. Derivative means you're comparing things. So then the derivative error multiplied by 100 will give you the together. Okay. So the leader
if you're talking about relative density, you get to compare the density of a substance with the density of maybe water as yeah. So that tells you that it's relative because of the comparison that you're making. So you're trying to find the ratio of the absolute error to the true value. That's your derivative error. Then for the percentage, you just multiply by 100, the derivative error. Are we together? Okay, then there are what we call experimental errors. The errors that you get to make when you're doing the errors that you things that lead to you making errors in a there are different errors that you can make or that can be made. So there are what we call systematic and also random errors. So usually the random errors are usually small and they don't usually have a very big effect on the solution or the answer that you have to find. But the systematic may be big. Okay? So systematic errors produces values that are either higher or lower than the true value. The error is often caused by a fault with the you're using to take measurements. It can be caused by the device, okay, or maybe a consistent mistake in taking reading. So maybe you, as somebody who is doing the experiment, you are taking long measurements, okay. So we can say lack of experience, inexperience from the experimenter, wrong readings, and other things. So they can lead to what we call systematic errors. Then random errors, actually, these are the errors that occur, usually are not systematic errors. When what you've done is right, all the things that you've done are correct, you've taken the right measurements, the devices that you're working with are all okay. So you may still find that there are some differences in terms of the true value. So those are random errors and they are usually very small. Are we together? Maybe the true value is for example 2.9, then you get to find maybe 2.86. So there are some random errors that you can't even predict. So systematic errors, you're able to identify them. It's possible, you can identify them. Random errors, you can't know them.
Are we together? In such a case, we can say the fact that we're